Intermediate Algebra, Section 11.3, Infinite Geometric Series. Suppose we consider the sum of the terms of an infinite geometric sequence, such as 3 plus 6 plus 12 plus 24, and so on. We get what is called an infinite geometric series. Here, as our n increases, the sum of the first terms, S of n, increases without bound because the numbers are getting larger and larger. If you notice here, the common ratio 6 divided by 3 gives us 2. The numbers are getting larger and larger and larger, and as a result, the sum of this geometric sequence would continue, as I said, without bound. So to find the sum here, we would say it doesn't exist or increases without bound. In this example, notice that the common ratio, 1/4 divided by the preceding term, gives us 1/4 divided by 1/2, invert and multiply, which ends up giving us 2/4 or 1/2. These values are getting smaller and smaller as we add this geometric sequence, and as they get smaller and smaller, they will approach 0. So whatever this sum is, it will have some value, but it will get stationary because of the fact these values are, each term further out is getting smaller and smaller and ends up approaching 0. Let's look at some of the first values. For example, the sum of the first term is 1/2. The sum of the first two terms would be 1/2 plus 1/4, which ends up with 3/4 or 0.75. The sum of the first three terms, again, 1/2 plus 1/4 plus 1/8, getting smaller, ends up being 7/8 or 0.875. The sum of the first four terms, 1/2 plus 1/16, results in a sum of 15/16. As you notice, our leaps aren't as large as they previously were, and we have a value of 0.9375, and we've only added first four terms together, and we're talking about an infinite sum here. If you look at the sums that we got for these first terms, the denominator of each of the sums is 2 to the n power. Here it's 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, where the numerator ends up being 1 less than that number. And if we continue with these values, we end up finding that the sum of this geometric series has a limit, and that limit is equal to 1. We're getting close to 1 here, and like I said, we only are looking at 4 terms. So for this example, our sum is equal to 1, and we have a formula for a geometric series when we're looking for the series having an infinite number of terms. Has a condition. For the absolute value of the common ratio must be less than 1. The limit of an infinite geometric series then is found and designated by S sub infinity is a sub 1 over 1 minus r. If the common ratio and the absolute value of that is greater than or equal to 1, then no limit exists. And that was that first problem that we had. So let's verify that here. We have determined that our ratio is 1/2, and if we were looking for this sum and using that formula for an infinite geometric series, and we've met the condition that our ratio, the absolute value of the ratio, is less than 1, we take the first term, which is 1/2, over 1 minus the common ratio, which is 1/2. Simplifying in the denominator, 1 minus 1/2, or 2 halves minus 1/2 is 1/2. We have 1/2 divided by 1/2 is equal to 1. So there we have proof of that using the formula. They're asking us to find the sum of these infinite geometric series. They're adding these together. Well, before we can find the sum, we need to know what the common ratio is to see whether there is actually a sum here. So common ratio, taking a term divided by the preceding term. We have a common 5, and a positive divided by a negative is a negative. That has no bearing, but the size of the ratio does, and this reduces to 3/2, which decimal-wise is 1.5. And what is the case here, there is no limit because the absolute value of our ratio is greater than or equal to 1. We have a 1.5. These numbers are getting larger and larger, and this probably should be a plus here. These numbers are getting larger and larger, and so even though they're positive and negative, this sum will eventually head towards infinity itself. So no limit exists. In this example, we have an infinite sum that they're asking us to find. Does it exist? Well, to determine that, we need to look for a common ratio. So we'll take 800 over the preceding term, 1,000. This reduces down. If we divide by 100, we have 8/10, and if we divide and simplify further, we end up, or reduce, we end up with 4/5. This ratio is less than 1. That means that the infinite geometric series does exist. And as you can see, these numbers are getting smaller and smaller. They're large, so our sum will be large. But at some point, we will be adding a series of essentially zeros, which will not change our sum. That's what allows us to find the sum of this infinite geometric series, found by taking the first term over 1 minus the common ratio. So our first term is 1,000. 1 minus the common ratio. 1 is the same as 5/5. 5/5 minus 1/5 will leave, or 4/5 will leave a 1/5 in the denominator. And when we take 1,000 divided by 1/5, we can invert and multiply, but let me write that. We have 1,000 divided by 1/5 is the same as 1,000 times the reciprocal, which is 5 over 1, resulting in 5,000 is where the sum of this geometric infinite series targets in on and won't change any further. We can use the property of infinite geometric series to convert a repeating decimal into a fraction. And that's what they're asking us to do here in this example. I'm going to split this apart as 2, the whole number, plus 0.54 plus 0.0054 plus 0.00054 plus ... If we add these together, it's equivalent to this repeating decimal here, and we're going to concentrate on finding the representation for this series here. Is it geometric? Well, to find the common ratio, we'll take a term over the preceding term. When you do your division and simplify, we end up with a common ratio of 1/100th. This meets the criteria for the limit of an infinite geometric series. So for this portion, that series or sum of this infinite geometric series is found by taking the first term over 1 minus the common ratio. First term is 0.54, 1 minus 0.01. Simplifying in the denominator leaves us with 0.99. Simplifying this fraction, since we want a fraction notation, we're not going to do division, rather we'll reduce the fraction. We have decimals, and to make this easier, we can turn it into a 54 over 99 by multiplying top and bottom by 100, and then recognizing there's a common 9, which 54 divided by 9 is 6, 99 divided by 9 is 11. So the decimal portion of this number is 6/11. We have a 2, and so our final answer will be 2 and 6/11 would be the fractional representation of this number.